show his endeavor to design of a learning machine that leverages the physical models which can extract patterns from the experimental data. So I will left the platform to Dr. Maziar Raissi. And also if we have any questions, we would like to leave the question after the talk. And I will record any questions if you left messages in the chat. So thank you. I will left the screen to Dr. Raissi.
Oh, thank you, Kai, for the invitation and the nice introduction. And do you guys see my screen?
Yes, I could see the screen.
And do you see the video?
Correct, video flows.
Okay, perfect. So today I'm going to be talking about hidden physics models. It's actually not a single paper, but it's a combination of a lot of papers. Everything started at Brown with this project, where we wanted to design super cavitating hydrofoils. Basically, given enough speed, this vessel is gonna start flying in water. It's actually not flying in water, to be honest. It's flying in the air, because as it goes fast, it's gonna create vapor around these hydrofoils. So these are super cavitating hydrofoils. And once you have vapor, you're basically flying in the air. This is external flow. And everything ended with this paper. That's an internal flow. This is the aneurysm of a real patient. This is behind the left eye. And we were trying to simulate some data that are coming out of 4D MRI or CT scan. Given that data, we were interested in understanding the internals of the fluid, like what is the velocity, what is the pressure, how do the streamlines are going to look like, and what is the shear stress on the wall of the aneurysm. And this is your data. That's the output of the algorithm. Okay, what I'm not going to be talking about today are about image classification. I'm not going to be talking about natural language processing or generative adversarial neural networks. But why am I including this slide? The reason is, even in our images, there is physics. For instance, if you take this airplane and you push it to the right or up or left or down, the class is still going to be an airplane. If you take this bird and you push it to the right, left, so these convolutional neural networks, they work not because of random reasons, but because there is inductive bias in them. The same thing happens in natural language processing. When you want to do translation, there is inductive bias. So you need to know the order. Even if you are using a model like transformer, the order matters. And you're going to do that through positional encoding, etc. So the order matters. And you need to encode that. And the same way, if you're learning high dimensional data sets like images, then convolutional neural networks are a good choice in addition to generative adversarial neural networks, because that's going to give you the high level distribution of your data. And again, there are some invariances there that you're using, in particular for the images. But there is a catch here. In our field, scientific computing, we don't have enough data. So we have to learn how to work with smaller size data sets. And this is exactly the case that we had for the super cavitating hydrofoil problem that I mentioned. We wanted to design this. That was being funded by DARPA. That's the vessel, the marine vessel that we were designing. We started with the hydrofoil, and then we ended up designing the entire vessel and putting it in water and testing it, actually. But let's start with the super cavitating hydrofoil to at least explain the methodology that we used. And let's parameterize that. Let's draw some engineering figures and cut the vessel, do a 2D cross section. Once you do the 2D cross section, you can parameterize the 2D part with around 16 parameters explaining your splines. So you're gonna have 16 parameters here, and then you're gonna have an additional parameter here that you need to optimize. And then there is the angle in the Z direction. So you just parameterize this, and you find a good way to parameterize your geometry. Once you do that, once you have you parameterize that, if you keep changing these parameters, you're gonna need to do a simulation. You do a simulation, and that's gonna give you your lift over drag. And we were doing RANS models for this. And our framework, our solver was taking around 6 hours to give us pairs of, if we give it an input geometry, it would take the algorithm 6 hours to give us the corresponding label, the corresponding lift over drag. So one might say, why simulated data? Why not real data? The problem is that if you want to obtain real data on this marine vessel, you need to first design it, you put it in water, and then collect real data on that, which is super expensive. So it is not doable, it is not feasible. And the simulation is gonna be your data, okay? We wanted to go the route of data efficiency, started with Gaussian processes because they are data efficient by construction. Like any other machine learning framework, you're gonna have four components: data, prior, training, prediction. For data, it was a regression problem for us. We had an input shape, an input geometry, and then the corresponding output lift over drag. And then these are noisy observations of some underlying function, which we don't know. And it's gonna look nicer if you put them in vector notation. Y is equal to f of x plus epsilon, and x is now a long matrix. And as I mentioned, if you knew f, you wouldn't need any simulations at all. You wouldn't need any real data at all. Your problem would have been solved. So you need to know what is f. And f, we started with Gaussian processes. F is a Gaussian process with some mean and some kernel. But what is a Gaussian process? What is that notation? It is just a shorthand notation for saying that if you take 2 points and look at the corresponding values, they are gonna be normally distributed with mean 0 and some covariances. The covariance of x and x and x prime and x prime, etc. But then rather than writing this notation all the time, you're gonna say f of x, 0, k of x prime. And a typical example for this kernel is the squared exponential kernel. What does it say? If 2 points are really far apart from each other, if this distance is huge, then this exponential, in addition, with the help of this negative sign, is gonna make the covariance of those 2 points to go to 0. So maybe that's a good assumption, maybe that's a bad assumption, but that's an assumption that we are gonna work with. The choice of the kernel is similar to the choice of the basis functions that you have in scientific computing. For instance, you have the option to work with sine functions, cosine function, Fourier basis. You have the option to work with finite element type basis, first order, second order, polynomial order of any order. So that's a choice that you make. And that's why it's called prior. It's a choice that we make. Training, the objective of the training is to come up with the best hyperparameters. So here, what is the best gamma and what is the best omega? Everything was normal Your data assumption is normal. Your model is normal. It means that your data is gonna have a mean 0. It's gonna be normally distributed and a covariance matrix. So this is now a matrix coming out of evaluating your covariance function on your data, and then adding this part of the noise. Okay, whenever you have a distribution, that's gonna give you your likelihood. And we want to maximize the likelihood with respect to theta and sigma. And that's exactly what we want to do. You can either maximize the likelihood or minimize the negative of the log of the likelihood. We take the log because this normal distribution has an exponential. So log is gonna cancel the exponential. And then you multiply by a negative because in machine learning, we like to minimize rather than maximize. And you're gonna end up with two terms. One is trying to fit the data as close as possible. So it's a data fitting regime. And the other term is trying to penalize the complexity of the model. And that's why Gaussian processes are data efficient, exactly because of this log determinant term. So they have a regularization term built into them by construction. So you fit the data and you want to find the model that is simplest and is explaining your data the best. So you have two objective functions here. One is fitting the data, the other one is finding the simplest model. And in terms of prediction, somebody gives you a new shape, a new geometry. We have two options. Given that geometry, we can go ahead and build a vessel, put it in water, collect the corresponding lift over drag. Or you can take that geometry, push it through your simulator, and that's gonna give you the corresponding lift over drag. That's another alternative option. And these two options are really expensive. The third option is to call your Gaussian process, to do predictions using your Gaussian process. This is a new geometry. We want to know the corresponding lift over drag. We have some data. That is our assumptions. You can go ahead and condition on the data. You condition on the input and output data. It's gonna give you a mean and a standard deviation. So some people, when they see this slide, they say, why do you start with a 0 prior? Why don't you put a neural network there? You can actually do it. And we are gonna do it later on. But even a 0, even if you put 0 here, your posterior is gonna have a non-zero mean, okay? And if you write it down, it is gonna give you K of X star and your data, K inverse Y. And if you call K inverse Y to be some alpha, a vector alpha, you're saying alpha times this K. This is a vector, that's another vector. You can write the summation over your data. You can expand it out. And that's gonna give you the summation of alpha i's, K of X star and Xi. And this K is this exponential function. This is, if you don't do Gaussian processes, this is an RBF basis function, basically. So you're expanding your result in terms of a bunch of RBF bases. And that's why whenever I see a kernel, I see a basis function. There is one-to-one correspondence between the two. Not only you get a mean, you get a variance. So some people confuse Gaussian processes with Kriging. They are similar, but they are at the same time different. The difference is this training process. So for Kriging, these parameters are fixed, or some choices that you make. Here you have an objective function to train them. And the other one is this uncertainty that is coming out of it. And let's see an example. Let's say X is the space of the shapes. We know that the space of the shapes was high dimensional, was at least 16 dimensional, but you can project everything into one dimension for visualization purposes. So we are putting this to be our shape. This is our lift over drag. And any red circle that you see, is a pair of simulations that you did. You chose a geometry, you solved your problem, you did your simulation, it took you 6 hours, and you came up with this data point, the corresponding lift over drag. You had another geometry, you did the same thing. You had another geometry, it took you 6 hours to come up with the corresponding label. If we knew the blue curve, our problem would have been solved. So we don't know the blue curve. The blue curve, only the nature knows. We don't know it. All we see are this data. The dashed red lines are coming out of the predictions of the Gaussian process. And as you can see, the mean is non-zero. It's exactly what you have for your function. And the other part is the two standard deviation that you can use. So why do you need the variance? Why is it useful? Because now you can do Bayesian optimization. We wanted to come up with the best geometry that is giving us the highest lift over drag. So we are going after this peak. But the blue curve we don't see. If we see it, the problem is solved. What do? You do two simulations or a couple of simulations to start with. You start with two simulations. You do your Gaussian process regression on those two data. That's gonna be a very bad prediction. But what you can do is you take the mean of this prediction, you add the two standard deviation to it. This is where the standard deviation is gonna help us. And that's gonna give us an upper confidence bound. This curve, the blue curve, we cannot optimize. These data points, you cannot optimize. They are discrete and you don't have enough of them. But the red curve here is your acquisition function and you can optimize it. You know it everywhere. So let's go ahead and optimize that. Find the maximum of that. That's gonna tell us, go ahead and sample next here. Have you tried this geometry? If not, try it and see what lift over drag you're gonna get. Do your simulation and look at the lift over drag. We're gonna do that. It's gonna give us a new data point. The surrogate is gonna optimize, it's gonna get better. And then the next step is go ahead and sample next here. And you keep doing that. Sometimes you're exploring because the model is too uncertain about what is happening in this regime. Maybe the maximum is there, maybe it's not. But let's try to look there and reduce the uncertainty. Sometimes you're exploring, the uncertainty is huge. You reduce the uncertainty, and then keep focusing. Sometimes you're exploiting, explore, exploit, explore, exploit. And then you don't need to explore your entire space. You don't care what is happening inside this regime anymore. And you are being sample efficient by not caring what is happening here. Because the uncertainty is small enough for you to say the maximum is not there. Don't look there. The maximum is here. So that was single fidelity model. We also had another model, which was potential flow. It would take us 6 minutes rather than 6 hours to do the simulation. If something is cheap, it is probably less accurate. So that's a low fidelity model. Cheaper, less accurate. The high fidelity model was more expensive, more accurate. So there is always this trade-off between accuracy and cost. And the idea was, can you use both of them? And this is exactly what we wanted to do. Rather than doing simulations that take 6 hours, let's do simulations that take 6 minutes and use that. So here I'm gonna keep adding data points to the figure on the left, and the figure on the right is gonna get better each time. And we are trying to approximate this function that we don't know, this blue curve. Let's keep adding points to the left. 3 points, 6 points, and the data on the right is not changing. It's the same data, but the prediction is changing. And then after a couple of iterations, you're gonna nail the function on the right. But how is this possible? With a simple model. This is actually a simple model that we were using. you can make an assumption that the high fidelity function is a linear combination of your low fidelity functions. You can have multiple low fidelity codes. So this could be a vector. Your high fidelity function is a linear combination of your low fidelity functions plus a correction term. And everything we are gonna assume is a Gaussian process. They have their own hyperparameters. This is a simple assumption, but once you use that, it's gonna help you correlate low fidelity functions and high fidelity functions. So now that they are correlated, any sample that you add here is gonna update the figure on the right. The rest of it is the same process as Gaussian processes. So it's exactly the same process. You're changing your prior. This could be a bad prior. This could be a very good prior, but that's a choice that you make. And we actually have a paper that is improving upon that using neural networks. So you update your prior, make it more powerful. And that's exactly what we did here. You can start with a benchmark design that is already optimized using genetic algorithms. And you can actually make that design better and better. So that's a geometry, that's the corresponding drag over lift. So you might wonder, why are you minimizing here? Because previously we had lift over drag. This is drag over lift. We want to maximize lift over drag and equivalently minimize drag over lift. So far, so good. Here, up until now, the physics was only being used through data. So you had a simulator, you would simulate, you would generate data, and then your Gaussian process would just consume the data generated by you. Can you somehow encode your physics inside your Gaussian processes so that you don't have to call your simulator anymore? Can you encode them explicitly in your Gaussian process? We know that those simulators are simulating Navier-Stokes, and we know the equations for Navier-Stokes. Can we encode them in our Gaussian process and make our prior more smart? So this is, let's say this is your physics, Berger's equation. Let's go ahead and discretize it. Backward Euler, un minus 1 divided by delta t is your right-hand side. Let's approximate un by a Gaussian process. Let's put a Gaussian process prior on un and push it through this differential equation. And then you can write down the correlation between yesterday and today. You can write down the correlation between un and un minus 1. And here we are using symbolic differentiation, mathematical, maple. They're gonna take symbolic differentiations. But now you're taking the derivatives of your kernel. You take the derivative once, there is delta t here, there is un minus 1. You take a derivative of your kernel with respect to x, and derivative of your kernel twice with respect to x. Now, the physics is inside this prior. What is the definition of physics-informed prior? What do we mean? Any samples that you generate from this distribution, this prior, is gonna satisfy this relationship by construction. Any samples that you generate, any random samples that you generate is gonna satisfy your physics. Or at least your physics in addition to your discretization scheme. It's gonna satisfy that. And the main observation here is that the derivative of a Gaussian process is a Gaussian process. And that's what we are building on. The derivative of a Gaussian process is a Gaussian process with a different kernel, but it is still a Gaussian process. And how are you? We are not interested in any random sample from our prior. We are actually interested in our posterior. So somebody gives us some data, maybe the data are initial data and data on the boundary. And then you can train your Gaussian process. The rest of it is the same as before. Basically, you can think of, it is exactly very similar to multi-fidelity framework Yesterday is a low fidelity version of today. Today is a low fidelity version of tomorrow, etc. Somebody gives us some data, we condition on the data, we do some training, we condition on the data, we do some prediction. Okay, from this state to the next state, we are okay. But from this state to the next one, we are not okay because we don't have data. We don't have training data. What are we gonna do? We are gonna generate artificial data from our posterior distribution. So we are gonna sample from the posterior distribution. Randomly choose some locations. The corresponding locations, you're gonna sample from this distribution. You have a distribution. The difference between artificial data and training data is that training data is noisy, but certain. You know that this is noisy. Yes, this is a noisy observation, but you know the location forever. It's the same location. Yes, you made some mistakes in your measurements, but the mistakes are with you forever. By artificial data, any points that you sample here is gonna have a distribution, so it's uncertain. It has a mean and it has a variance. The rest of it is the same as before. Training, condition on the artificial data, predict, and push the uncertainty. There is a one-to-one correspondence between Kalman filters and numerical Gaussian processes, but Kalman filters are for finite dimensional systems, ODEs. This is for infinite dimensional systems, space of functions, partial differential equations, okay? If you write down the math, there is one-to-one correspondence. Especially when you see the prediction, there is a one-to-one correspondence between the math of Kalman filters and the math of numerical Gaussian processes. But this is for infinite dimensions. Some people ask me this question. You have the nonlinear dynamics of Berger's equation. You start with the Gaussian process. You push the Gaussian process through a nonlinear differential equation. So things should get non-Gaussian. The answer is no. Here, Gaussian processes are just function approximators. Think of them as function approximators. And the uncertainty is being propagated outside of the PDE. So it's being propagated outside of your PDE. So it's not gonna mess up with the nonlinear dynamics. It's not like you take a Gaussian process, push it through something nonlinear and get non-Gaussian behavior. And why do you get this S and N? You get it because your artificial data, they are noiseless, but they are uncertain. They have a mean, they have a variance. So you have to propagate the variance, the uncertainty. So far, we were solving forward problems. Can you use the exact same framework to solve inverse problems? And the answer is yes. Let's say you know your equation, but you know it up until some parameters. Here you have 3 parameters, but you could have infinitely, actually many parameters, not infinitely many, a lot of parameters. The same framework is gonna work. Discretize over time, approximate UN by Gaussian process, push the Gaussian process through your differential equation. Regardless of the number of derivatives that you're gonna take, you're gonna still end up with some covariances. And then the covariance is gonna mimic the behavior of your differential equation, K plus delta T, Kx, Kxx, Kxxxx. And this is a physics-informed prior. Something nice happens. The same way that in the forward equations, we were optimizing over thetas to come up with the best basis function, the same way you're gonna optimize over lambda 1, lambda 2, and lambda 3. So these lambda 1, lambda 2, and lambda 3, the parameters of your partial differential equation, turn into hyperparameters of your kernel. The same maximum likelihood framework that was giving you theta is gonna give you lambda 1, lambda 2, and lambda 3. And you can apply this to the Koromatov-Sivashinsky equation. Take 2 snapshots. This is the entire data set. We are not using that. We are using only 2 snapshots at this time and at that time. And then you manage to estimate these parameters, even in the presence of noise. So there are some other papers that are using the entire data set, and they are adding noise. And because Koromatov-Sivashinsky equation is a nasty equation, it can turn into being chaotic. They don't get good behavior. They don't get good results for these parameter estimates in the presence of noise. But here we don't have that behavior because we are taking derivatives of our prior. We don't take derivatives of the data, okay? And we are not using finite differencing. So somebody might say, why is your framework data efficient? And the answer is Gaussian processes are data efficient by construction. So it has nothing to do with us. We just use Gaussian processes. The other one is we are physics informing it. Many of the priors that you could imagine are not going to happen here. So you're reducing the size of your possibilities, the space of possibilities, or the possible functions. That's why you get more data efficient. You can apply the same framework to Navier Stokes equations, flow past the cylinder, and then estimate the Reynolds number in addition to the advection coefficient. We try to apply that framework to real data, actually experimental data set, and the framework failed for good reasons, because the physics here matters. There is no guarantee that the experiment that we were setting up is Newtonian. It could be non-Newtonian because this is a soap film. And the other observation is that in this experiment, these test sections are vertical. So we need to take into account the effect of gravity. So there's a cost to physics informing your neural networks. Your physics needs to be correct. So far, machine learning was helping us. Gaussian processes was helping us, but Gaussian processes, can we help them? They don't scale good to big data. And the answer is yes. There is this parametric Gaussian process technique that is gonna rely on this idea. You're gonna have a parametric Gaussian process that's gonna see your real data and it's gonna process it in mini batches. And you have a classical Gaussian process in its classical form that is seeing your artificial data. So the role of the parametric Gaussian process is to generate data for the classical Gaussian process. And if you have a smaller size data, if you can summarize your big data in a smaller size, then you can use Gaussian processes. And the idea of this paper is that is very simple, is that the prior, as soon as a bunch of data comes in, is going to give you a posterior. And now that posterior could be the prior for the next step. Prior, posterior, prior for this posterior. Prior condition on the data gives you a posterior. That posterior is now your prior for the next step. And this is actually how humans think. Some data comes in and we update our view of the world. You can apply this to satellite data, and whenever you have spatiotemporal data, that's going to be big data. And you can apply that to this data set. Can we do similar things using neural networks? Let's go over neural networks very quick, and then we are going to see what is the key observation. It's the same as before, the paradigm. Data, prior, training, prediction. Data is the same as before. Now what is going to change is how you're going to model F. We're going to say F is a linear combination of a bunch of bases. Okay, that's what we do in scientific computing. There's nothing wrong with that. But then the question is, what is HL? Are you going to use sine functions, cosine functions, hat functions, spectral element functions, etc.? You could say, how about learning that? You could say, let's repeat that process. HL is a linear combination of HL minus 1, a bunch of other bases, plus some bias. And if you do that without this nonlinearity, things are going to become very boring. A linear weight is going to get by another bunch of linear weights. You can just rename them, and then your entire model is going to be linear. To make it nonlinear and more interesting, you are going to add activation functions. It could be tanh, it could be ReLU, you name it. And then in the end, you reach your X. So the objective is that you're learning your basis functions. How do you learn them? Previously, for Gaussian processes, everything was happening at the covariance side. And as I promised, you can put your neural network on the mean of your distribution. And that's exactly what we are going to do. We are going to write our likelihood. That's going to give you that term. And if you expand it, your likelihood is nothing but the mean squared error. For neural networks, prediction is very easy. Somebody gives you a new geometry, you just evaluate your network, and that's done. There is no conditioning. GPs versus neural networks. Gaussian processes are non-parametric. Neural networks are parametric. GPs are not scalable to big data. Neural networks are. Gaussian processes quantify uncertainty. Neural networks don't. And GPs balance the trade-off between data fit and model complexity. Neural networks don't. So there are ways of making neural networks more data efficient. There are ways of making Gaussian processes scale to big data. And we saw an example, but these are the extremes of the story. So let's try to use neural networks for these types of problems. So it's going to be the same framework. For forward problems, in the regime where you have small data and physics-based. For inverse problems, where you know something about your physics and your data as a consequence needs to be bigger. And if you have enough data, actually, you can learn your physics. There is no need for physics at all. You can learn it from scratch, given enough data. This is where deep learning is shining. This is where physics-informed deep learning is helping. And this is my favorite, where you are doing, when you know something about your physics and you have some medium-sized data. So let's use neural networks. What is the key observation for neural networks? The key observation for Gaussian processes was that the derivative of a Gaussian process is a Gaussian process. Here, the derivative of a neural network is a neural network. Let's say that's your physics. We are going to go ahead and approximate the function that takes time and x as input and it's outputting u by a neural network. We are going to take the derivatives. We're going to create the residual. And then we are going to write down our Berger's function, Berger's equation. We're going to return it. Again, any samples that you generate from these pairs of functions, u and f, they are going to satisfy the Berger's equation by construction. So they're going to satisfy this relationship. Any pair of samples by construction is going to satisfy that. But the problem is you're not interested in any f, you're interested in a particular f. Sometimes your forcing is 0, sometimes it is non-zero, but you're interested in a particular f, and that's where the training is going to come in. You need f to be 0. So you're going to enforce your equation to be 0 at a bunch of collocation points. So these points you can have as many of them as you need. You can have infinitely many of them. Your boundary condition and initial condition are going to go in this term of your loss function. You optimize that loss and you can solve Berger's equation. You can solve Schrödinger equation, the same pattern, but I'm including this slide here because this part of the neural network is very boring. It's fully connected, nothing special, okay? But these parts, the red ones, are non-trivial. Once you take a derivative of u with respect to time, you're taking this portion of your network, transposing it, and then putting it on top of your previous network. And you change your activation. You take derivatives of your activation functions. And that's what backpropagation is going to do. It means that if you start with a network that is 10 layers deep, after this operation, it's going to become 20 layers deep. After taking the derivatives twice, it's going to become 40 layers deep. So these neural networks are going to become deep depending on the network structure, depending on the number of derivatives that you have. This slide I'm going to skip. It is just to compare finite elements, finite volume, finite difference to pins and reduced order models. Basically, rather than using basis functions, you can learn your basis functions. And rather than discretizing your differential operators, you can use automatic differentiation. And the relationship between pins and ROMs is that you can do transfer learning. Maybe you learned something from a particular geometry, you can transfer it to a new geometry. And that's exactly what reduced order models do. You choose your basis smartly based on your previous experience, maybe based on previous time steps or previous geometries that your algorithm saw. Can you use the same framework for solving high dimensional problems? This one I'm gonna skip. The answer is yes, you can solve 100 dimensional Black-Scholes, you can solve 100 dimensional Hamilton-Jacobi-Bellman, and these are the type of problems that you cannot solve using finite differencing. Because in 1D, you can put 10 points. In 2D, you need to put 10 to the power 2 points. In 3D, you're gonna have a mesh of the size of 10 to the power 3 points. And then soon, you're gonna run into the curse of dimensionality. But here, through the proper choice of your loss function, a nice theorem, which is not mine, and the proper way of approximating your functions with neural networks, and the relationship with the forward-backward stochastic differential equation, you can span your space in a smart way, and then you can solve these problems. You can get rid of the curse of dimensionality. Can you do inverse problems and data assimilation problems? The answer is yes, exactly the same framework as before. You collect data behind the cylinder, and that's gonna give you not only your velocity, but also your pressure and these coefficients. So one thing that was surprising out of this paper at that time was we had absolutely no data on the pressure. How is the algorithm able to give us the pressure? It turns out that you're getting the pressure through solving these equations explicitly. So it actually implicitly through the optimization, you're solving for these equations. And that's why you're getting the pressure out, and it's off by constant because the pressure is unique up until an additive constant. So that was a nice observation. And we said, can we apply that to a more complicated geometry and use particles? The method worked, but it is not something that is publishable, and it's not something that is usable. The answer is, the problem is, you cannot inject particles in somebody's arteries. That's gonna kill them. But you can actually inject dye in somebody's arteries and do your images. And that's what we do all the time. We inject dye, we do 4D MRI, or we do CT scan. And what is the dynamics of a dye? It is a passive scalar. It's gonna travel by your fluid. It's gonna diffuse according to its own diffusion constant. And that's where the Peclet number is gonna come in. And then it has no effects on the dynamics of the velocity or the pressure. We are gonna use this data. The rest of it is gonna come out of physics. So this was just some experiments to make sure that the algorithm is working. And at the same time, we don't want to give it boundary conditions. We want it to be boundary agnostic. We don't want it to give it initial condition. That's the entire thing. That's the entire data that it should work with. The algorithm worked. It was promising for Peclet number being equal to the Reynolds number. Reynolds number was 100. Being smaller than the Reynolds number and being bigger than the Reynolds number. So the Peclet number doesn't really matter. You can actually learn it from this data. You can actually learn not only the Peclet number, you can actually learn the Reynolds number as well, or the fluid property. And this is exactly the framework that we're going to use to help us go to devise a patient-specific framework. So a patient goes in, they're going to do 4D MRI. By 4D, I mean there is time and space. So this one, there is time and space. You are just measuring the concentration of the dye in that person's artery. This is the aneurysm behind somebody's eye. So, and it's being cut out of the entire arterial system of a human being. So there is no good answers for what is a boundary condition here. What is the boundary condition here? So we need to be boundary condition agnostic. We need to be geometry agnostic, and we need to be able to work with this data. This data is the only data that you have on this neural network. Your data is here. So you don't have any data on U, V, W, and P. And for those of you who do neural networks, you know that if you don't have data on an output of a neural network, there is no way to learn it. So there is no way to learn it from you. There is no data to learn. To compensate for the absence of data, we have equations. These are Navier-Stokes equations. You use them. You have 5 equations. You penalize them. You make them 0. And then the velocity and the pressure is going to come out. And in the paper, we are reporting the actual shear stress on the wall of the aneurysm. And once the doctors know the shear stress, they know it's more information for them to decide how severe that aneurysm is. Do they need to operate or no? So this is a non-intrusive patient-specific framework. We can apply this to multi-physics problems. Flow past the cylinder. These are useful for deep sea risers. So now you have 2 dynamics. One is the Navier-Stokes, and the other one is the dynamics of the solid. It's a fluid solid interaction problem. You can do Eulerian and Lagrangian, basically couple a PDE and an ODE. That's your data. Given that data, give me the velocity and the pressure. You can do turbulence. It turns out that it's better to model the distribution of the turbulence rather than its trajectories. So in this work, we are modeling the probability of the probability distribution of those trajectories of the turbulence. And there is a nice paper by Peyman that takes this P and analytically it's going to give you this exact D. So given P, we want to know what is D. For us, it was a neural network where you have data on P, but you don't know your D. To compensate for the lack of data on D, you can write down an equation, put it in your loss function, and optimize. And that's going to give you the same result, or very close. For the model, I have 2 more slides, and then it's done. For model discovery, you have enough data. Let's start simple. Let's say you know x dot is equal to f of x. And let's say you don't know f. You don't know your dynamics. Can you learn your dynamics? And what is your loss function? The loss function is going to come out of discretizing this equation, trapezoidal rule. We are going to approximate f by neural network. Now we are going to give it data, train f. One of them is the exact dynamics of the Lorentz system. The other one is the learned dynamics. For Lorentz system, it's chaotic. So there is no hope for you to get the trajectories right, every single trajectory, but there is hope for you to get the attractors, get the big picture correct. And you're getting the big picture correct. You can do Hopf bifurcation. You can do glycolytic oscillator. This is typical of biological systems. Actually, this framework you can apply to COVID dynamics, SIR models. Or you can do Navier-Stokes in a lower dimension. Basically, here you are reducing the dimension of the velocity field to 3 dimensions. So you're doing POD. You can actually learn infinite dimensional dynamical systems the same way that before you were approximating U by a neural network. You can approximate N by yet another neural network. So this neural network F that is gonna come out of automatic differentiation is gonna be physics informed, but you don't know your physics. Your physics is, there's a question mark here. And you're gonna approximate by yet another neural network, and then the framework is the same as before. Somebody gives you some data, you know your equations. Actually, you don't know your equation, to be honest. You're learning N. Once you learn N, basically you can learn the dynamics of Berger's equation. You can learn the dynamics of Berger's equation when the initial condition is different. So the training is happening there. The testing is happening here. And then you can learn KDV, Koromoto-Sivashinsky, Navier-Stokes, etc. And for many of the things that I explained today, I don't have any proofs. There are some papers coming out recently that are doing the mathematics of these types of frameworks, but I don't have any proofs. All I have are these codes that I can share online, and then you can test whether I'm telling you the truth or no. You can just download the code, clone it, and then run the code and see if we get the same results or no. So it's for being reproducible. Okay, I guess we can, I can stop here. Thank you for your attention.